the speaker is studying in METU and working in TED University as a research assistant. So his name is Arsham, and Sinem, would you please kindly read his resume for us?
Okay, hocam. Arsham Atashi Khoei is a PhD student in Industrial Engineering Department of Middle East Technical University. He received his bachelor and master degrees from Industrial Engineering in Iran. Currently, he is working at Industrial Engineering Department of TED University as a research assistant. His recent research areas include green logistics, green warehousing, focusing on carbon dioxide emission concerns in location problems and routing problems in distribution systems.
Okay.
Thank you.
Arsham, thank you for being here. I see 100 slides. If you are planning to go all of them, you may run out of your time. So we have 50 minutes.
50 minutes, yes.
We can reserve some time for the questions and answers as well. So please be careful to use your time. So 100 slides. I hope it's a typo there. So good luck.
Thank you. Thank you, and thank you for all of the participants for this seminar. Although I have several seminars and presentation about my studies, but again, it's a stressful area here to present my studies and works. I will try to go very fast over all of the subjects and the slides here. So this presentation is about some of my works in PhD studies with my advisors and co-advisors, Haldun Sural Hoca and Mustafa Kemal Tural. And my presentation is about Green-Weber problems, actually Green-Weber problem and its extension. So I will continue with a brief literature review about green logistics, and I will review Weber problem. Then I will give some remarks on second-order comprogramming, and then I will provide the Green-Weber problem and the computational experiments and analysis on this problem. Similarly, I will provide the multifacility Green-Weber problem and the solution approaches and the computational experiments on this problem. Finally, I will conclude my presentation with some other study directions. So we know that nowadays all over the world, we have a significant increase in demand of the goods and services for the customers, and accordingly, the distribution and transportation related activities for these demands are growing. And the corresponding delivering and picking goods activities for satisfying customers result in significant amount of CO2 emissions of fossil fuel combustion, and this affects the climate and citizens' quality of life. On the other hand, we have some other studies such as green logistics, which is the study of practices that take environmental and social impacts of logistics operations into account. So here we have several studies in green logistics that take emission into account at the operational and tactical levels, such as the studies I am presenting here. For example, Bektaş and Laporte introduced for the first time the pollution routing problem that minimizes fuel emission and driver costs in VRP with time window issue, let's say. And their solution for solving this problem was based on the discretization of the speeds on the roads, and also they ignore a part of the fuel consumption formula in their formulation and model. They are able to solve instances with up to 20 customers within 3 hours with their formulation. Later, Emrah Demir and the others develop an algorithm for solving the PRP that could solve instances with 200 customers in approximately 10 minutes. And finally, not to say finally, but finally in this slide, the same authors in 2014 provide and introduced a bi-objective PRP that in this study they believe that CO2 emission and the driver's wages are they consider these two objectives as two conflicting objectives. So these are some studies at the operational and tactical levels. But let's see let's see what is Weber problem, which is a facility location problem that can be widely considered as strategic level problem. In this problem, we locate a facility on the plane which will serve a number of customers. These customers have demands or weights, and the aim is to minimize the sum of weighted Euclidean distances between the customers and facilities. For example, in an example here, in this figure, I show you a number of customers in black dots, let's say, and the optimal location of a single facility on the plane is shown with a red square, which can be obtained with some related solution approaches for the Weber problem that I will talk later. And we have a multi-facility Weber problem. For example, in this figure, I show you an instance with the same customers, and we have, for example, 4 facilities that are located to serve the customers here. And similarly, customers have demands and weights, and we minimize the sum of Euclidean distances between the customers and the allocated facilities. So we can model the Weber problem with single facility. We just an objective function here which minimizes the Euclidean which minimizes sum of weighted Euclidean distances between the customers and the facility. For this problem, there's a widely known and used Weisfeld method that iteratively solve the problem. And also we can consider second-order comp programming for this problem. What is second-order comp programming? It is actually a generalization of linear programming, and so it can solve the problems in polynomial time. And every problem in this form can be rewritten as the second-order comp programming formulations. With SOCP formulations, we can model the Weber problem with the minimization of sum of weighted distances. That distances are also equal to Euclidean distances of the customers, between the customers and the facility in the optimal solution. So what is a Green-Weber problem? Similar to Weber problem, we locate a facility on the plane which will serve n customers, a number of customers, and the customers have demands or weights, and we can call this parameter as the number of vehicles that will be sent to the customer I, let's say, and every customer I has time limits, or we can call it deadlines of Li, and our aim is here in the Green-Weber problem is to find the location of the single facility on the plane, and we will determine the speeds of the vehicles that will serve the customers within their deadlines, time limits, so as to minimize the CO2 emitted from the vehicles in this distribution system. So this formulation and this problem is nonlinear due to the Euclidean distance and the emission formulation. So our used emission formulation, which is used again in the literature, has nonlinear terms such as z over v or v square z, where z is the distance traversed with the vehicle, and v is the speed of the vehicle in this distance. But this formulation, when we have constant value for z, for example, 100 kilometer, this function is convex on the v variable. As you see, the function shape in this figure, for example, when we call it fuel consumption rate for per 100 kilometer, we have a minimum value of the emission for about speed of 55 kilometer per hour. So with this convex function, we are going to formulate the Green-Weber problem, but we have challenges with the nonlinear terms. First, let's simplify this formulation with for alpha parameters, and also we can just multiply these to a fuel emission cost constant to call it the objective function or function of cost of fuel emission cost. So we have nonlinear programming formulation for Green-Weber problem. As this formulation, we are going to minimize the sum of weighted, let's say, emission costs, where we have zi equal to the Euclidean distances, and with the second set of constraints, we satisfy the time limits of the customers, and with these constraints, the distances and the speeds and distances are in such a way that the deadlines are not even violated. So for this nonlinear programming, where we have zi over vi and vi square zi as the nonlinear terms, we introduce another variable, which is actually the travel time of vehicle I, and is equal to zi over vi. And with this substitution and introducing another auxiliary variable as gi, we have here linear objective function, but we have a set of nonlinear constraints, and we try to rewrite these set of constraints as second order cone constraints. We multiplied both sides with zi, and we have these set of constraints, and these set of constraints can be handled as second order cone constraints, but by two related constraints. So we add these final two sets of constraints instead of the nonlinear set of constraints, and we have finally the second order cone programming formulation for Green-Weber problem with linear objective function and two sets of second order cone constraints, where the time limits are satisfied by the travel time of the vehicles at the last set of constraints. So let's see the benefits of this problem to use instead of the Weber problem. For example, suppose that we have a square and we have 4 customers at each at the corners of this square with unique and identical weights. I mean, the weights of the and demands of the customers are equal all to 1. And of course, the solution of the Weber problem is at the center of this square. But we will see what happens with the Green-Weber problem when we have time limits and we will have the emissions for the vehicles. So we use the parameters that are introduced in the literature, and we have demands all of the customers equal to 1. And we will see what happens when the deadlines of the first 3 customers, 1, 2, and 3, are infinite, or we can say that they have no deadlines. But we will see what happens when the deadline of the forced customer is getting tighter, for example, to 10 hours, 8, 6, or 4, and so on. So as we said, at the left picture, we see that the solution of the Weber problem is at the center of the square. And if we have the deadline of the fourth customer also equal to infinite, so it will be the solution of the Green-Weber problem will be the same as the Weber problem. But if the deadline of the fourth customer get tighter to 10, to minimize the emission cost of the vehicles, the solution of the Green-Weber problem will get closer to the fourth customer. And as you see, we will have closer solutions for the facility with the tighter deadlines for the fourth customer. And we can see this analysis by the numerical table here. FEC columns show the fuel emission cost, and we have the speed of the vehicle sent to customer 4 as V4, and at the last row we see the deviations of the values corresponding to Green-Weber problem from the Weber problem. So we see that sorry, do we have so we see that when we have tighter deadlines for the customers as equal to 10 and tighter, so on, we have fuel emission costs for Green-Weber problem much less than the fuel emission costs for the solution of the Weber problem. And for example, when we have deadline of the fourth customer equal to 4, we have 20% saving in the fuel emission cost if we use Green-Weber problem. And the other thing here is that we have much less speed of the vehicle to be sent to the customer 4. For example, we have 50% less speed value for the when we have a Green-Weber problem compared to the Weber problem. So this was just an illustrative example here. And remember that we had optimal speed equal to about 55 kilometers. So when we use greater and larger speed values than 55, we have much more fuel emissions. Of course, if we have less speed values than the optimal speed, we will have again more fuel emission costs. Okay, so let's go further with some other real-world features to be added to this problem. We can have traffic congestion, time-dependent traffic congestions with in certain time periods, and each of these time periods, let's index them with m, which has each of which has a length of pm. For each of them, we have speed limits with the index of m again, and we have here new variables for all of the time periods and for all of the customers, as for example TIM, ZIM, and BIM, which correspond to the time of the vehicle I at spent at time period m, or distance of vehicle at time period m, or the speed of the vehicle at time period m. So you cannot hear me well? I saw some chat here. Or is it?
Arsham, sometimes I hear a voice like clockwork with your voice. So I couldn't follow your slides. That's all, but I don't know what Özgür Hoca heard.
Well, I have probably I have connection problems, so I don't want to interrupt. Please continue.
Okay.
So, but I'm having difficulty in following, but others can hear very well apparently. So continue, please, Arsham.
Okay, I will continue, and I will try to move very less here. Okay. So in these traffic congestion patterns, we suppose that the speed limits are not increasing. So we have the traffic congestions will not decrease, and it will result in the fact that there is no waiting time for the vehicles in the successive time periods. So with these assumptions, we give the formulation, of course, second order co-programming formulation for the time-dependent Green-Weber problem with some additional constraints and with several additional variables according to the time periods. And I'm not going to the details of this problem. It is similar to the Green-Weber problem. So let's suppose again that we have an instance with 500 customers on a square, and they are separated to 4 groups, each with 125 customers. And suppose that the customers in the 4th group has each has 1 hour time limit. And here we will have 2 patterns, 2 types of time dependency for the congestions. In TD-GWP2, we have 2 time periods with the corresponding speed restrictions. And in TD-GWP3, we have 3 time periods with different speed limits. So when we solve this instance with different problems, we will have different increased or decreased fuel emission costs. For example, if we solve this instance with Green-Weber problem, we will have about 8.5 decrease in the 8.5% decrease in the fuel emission cost compared to the Weber problem. And if we have time-dependent traffic congestion with 2 time periods, we will have about 17% increase in fuel emission cost, and the differences between the 2 types of the time-dependent patterns is about 12% in fuel emission cost. And if we analyze the speeds in these problems, in all of the time periods, we have average speed of the vehicles equal to 63 with 15% deviated from the optimal speed for Weber problem. And also with in the other problems, we see that we will have increase in the average speed of the first time period for different problems if we have more restrictions and limits of the speeds in the next time periods. I describe these tables very shortly. And if we have 1,000 customers and in an instance, and they are located totally randomly, and we have for all of them time limit as 1.5 hours. Here also we have comparison for Green-Weber problem and the time-dependent Green-Weber problems. When we have a time-dependent Green-Weber problem with 2 time periods, we will have 5.4 increase in fuel emission costs and 1.6 for the 3 time periods. Again, we will see that we have more average speed values for the vehicles, at the first time period when we have restrictions in the next time periods to satisfy the deadlines of the customers. So up to here, I'm also giving the reference for our study published up to here. And then we went on to consider a problem with multi-facilities, and let's call it multi-facility Greenweber problem. In this problem, we have P number of facilities to be located, and the aim is again to find the locations of P facilities on the plane and determine the speeds of the vehicles to send to the customers, and such that the total amount of CO2 emitted in the distribution center is minimized. So here we have binary variables to determine the allocations of the customers to the facilities, and we have Qij as the distance between customer I and facility J. The mixed integer nonlinear programming formulation is provided in this slide for the multi-facility Greenweber problem, and with similar techniques, we reformulate it as mixed integer second order comprogramming formulation. And this formulation is weak because we have big M values here, which is equal to maximum distance of customer I and other customers. And the formulation is highly symmetric on the indices of the facilities, and this causes the inflation in the size of the branch and boundaries. We apply symmetry breaking constraints, and let's say what happens with the applying of symmetry breaking constraints. Very briefly, in this table, I will show you the row of the instance with 25 customers and 3 facilities, for which we cannot solve the problem in, this is 4 hours. We cannot solve it in 4 hours with, I think, with the solver Cplex, but we can solve this problem with symmetry breaking constraints included in less than 2.5 hours. And another feature of the formulation is according to the time limits or the deadlines of the customers. For example, if we have no deadlines and we solve the problem with the MI-SOCP formulation, we cannot find any feasible integer solution for an instance with 20 customers and 5 facilities in 4 hours. But with wide time limits applied on the instance, we can solve the problem in about 4,000 seconds with the corresponding objective function values and the average speeds of the vehicles. And when we tighten the time limits of the customers more, we can solve the problem very faster in 1,800 seconds. I think it is about half an hour. And in this instance, we see that of course, the average speeds of the vehicles get larger, resulting in larger objective function value. And we saw here the effect of the deadlines on the computational time of the problem. And with this computational time, we need some other algorithms, heuristic algorithms, to solve the problem with larger instances. So we will have some algorithms to get ideas or to develop that we developed. For example, we developed local search algorithm here, and we got ideas from location allocation, transfer, and decomposition algorithms in the literature. Location allocation algorithm is known in the literature, in which we initialize with random locations of an initial solution in the convex hull of the customers, and it iteratively performs the allocation and location step. In the allocation step, we just allocate the customers to the nearest facilities, and in the location step, of course, in our problem, we solve P problems with single facilities with our SOCP Greenweber problem for the customers that are located for each facility. For example, if we create an initial random solution for an instance in that's I show here with 3 facilities in red boxes, after iterations of location allocation algorithm, we will have this solution. But numerically, I can state that in, for example, instances with 75 customers and 5 facilities, when we apply 500 replications, I mean with 500 initial solutions, we have time of each replication equal to 1.14 seconds, and we had average of 81 improvement in the objective function values obtained by the location allocation algorithms, and in 22% of the replications we got the best solution known. I call them as the best known solution because we found these solutions with the heuristic approaches, the proposed algorithm that I will explain in the next slides. So what happened to the objective function values of the initial random solutions? I'm showing here the histogram of the objective function values of the initial solutions, and we can see that there are just a few solutions with the objective function value of less than 1000 or equal about 400. But with the location allocation algorithm, we get the solutions much better than the initial solutions. For the instances with 75 customers and 10 facilities, again, we applied 100 replications with location allocation algorithm on the initial solutions. We had much more computational time for each replication. We had about 76% improvement on average with the location allocation algorithm, but here we could not obtain any best solution with the solutions of the location allocation algorithm. So we decided to continue to develop improvement algorithms to be applied on the solutions of the location allocation algorithm. We came up with an idea of local search in which we can draw circles around the facilities in a given solution, and we can suppose that we solve the MISOCP formulation with restricting the search space of the facilities in their own circles. So one of the benefits here is that we have restricted search space for the locations of facilities, and with this benefit we have 2 other tunings. First, we will have smaller BGM values in the formulation, and second, we can have fixed binary variables before solving the problem. And I will show you how we do these tunings. For example, suppose that we have such a solution in which we have 3 facilities, and we draw circles around the facilities, and the search spaces for the facilities in the new solutions are only inside these circles. So the big M value, for example, here for customer I and facility J is the largest distance that the facility J can have from customer I, so the big values are set in this way. Also, suppose that we have customer I, and here at the bottom facility J prime. So the nearest distance, the smallest distance that facility J prime can have from the customer I in the new solution, here is less than the largest distance that facility J can have in the new solution from customer I. So in this case, we can set a binary variable of allocation binary variable of Hij prime is equal to 0. With these pre-tunings, we can continue with the local search algorithm. And the local search algorithm performs like this with iterations, several iterations. It draws new circles, and it searches for the better solutions in the new search areas for the facilities. For example, here we got the final solution with the red crosses. To show the effect of the tunings in this table, in every column inside the tables, the computational time of the approach is given, the corresponding approach. And we see that, for example, for the instance with 30 customers and 2 facilities, we can solve it exactly with the MISO-CP formulation in about 1600 seconds. With the location allocation algorithm, of course, here we use 10 replications, but each replication on average takes less than 1 second, but the best solution is 2.6% deviated from the best solution, which is the exact solution. And when we apply local search over the location allocation solutions with no tuning, we will have about half an hour computational time, and we will have the best solution just 0.2 deviated from the optimal solution. And then we apply smaller big M values tuning and fixed binary variables tuning, and both of them we will have much better solution times with the local search algorithm, and we will reach to the optimal solution. But the thing here is the radii of the circles we have. So the logic here we used is, for example, the beta value, which is equal to the ratio of the search space to the original space, which is obtained with this function. So with this function, we just introduce a logic for determining the radii of the circles, and what differs with different radii of the circles. For example, with in an instance with 49 customers and 4 facilities, with 5 replications for each. And let's consider that we have 10% and 5% for the beta value. When we use 10% for beta value compared to the 5% one, we will have a little bit more improvement, which is 9.3 compared to 9.1 over the location allocation solutions. But with this beta value and greater radii of the circles, we will have a significant increase in the time, computational time for this algorithm. And we see that the computational time of this algorithm is not satisfactory. And we decided to use this algorithm inside and integrate it with another algorithm, which I will describe in later next slides. But for now, let's go to the transfer algorithm, in which we just transfer customer, a selected customer from the its currently allocated facility to the second closest facility. And in this algorithm, at the first, we can get worse solution, but applying location allocation to the new solution, we may have better solutions later. We modified this algorithm found in the literature for the selection in the selection part, in some parts, specifically in the selection parts of the customer. So here we select the facilities, of course, with the preference of the customers, which customers are close or near to the borders of the pairs of the facilities. And also we select and involve the speeds of the vehicles that are sent to the customers, because we believe that if the speeds of the vehicles to send to those customers is higher, so reallocation and better allocation of these customers in the new solution will affect and will benefit our the new solution more. So with some modifications, we applied transfer algorithm to our problem. And for example, in this figure, I show you how we do this algorithm. For example, customer that is allocated to the right side facility is reallocated to another facility which is in the left. And in the new solutions, with applying location allocation algorithm, we will have better solutions. So another algorithm I will describe is decomposition algorithm, which is I should describe it shortly. We split and decompose the instance with a given solution in a way that the customers that are allocated to a number of facilities, this number of facilities is of course less than the original problem. So we solve another problem with smaller groups of the customers. So any improvement in the smaller groups will improve the total and original solution. In our problem, we set the p-hat, the number of the facilities to decompose the customers equal to 2, and we use the developed and provided a local search heuristic to solve and to use as the optimization tool for each subproblem. Okay, so for example, in this given solution that we have 4 customers here, for the facilities at the bottom of the figure, we split and decompose the customers, and with the local search heuristic, we solve this instance for the smaller group, and we get a better solution with about 34% improvement in the objective function value. And we propose our solution approach with these steps. At the first step, we initialize with random solutions. Then we apply location allocation algorithm, and we improve the location allocation solutions with the transfer algorithm. And with the optimization tool of local search in the decomposition algorithm, we do the final improvements on the solutions of the transfer algorithm. So let's see the computational time at each step of our algorithm, integrated algorithm. For example, here we have instance with 49 customers and up to 10 facilities with 10 replications of the algorithm. We see a significant difference between the computational time of location allocation and the other improvement algorithms. But we will see that we will have improvement with those improvement algorithms over the location allocation solutions. The location allocation algorithm turns satisfactory improvements on the initial solutions. Then we apply the transfer algorithm and we get better solutions. With the bold values, I show you the improved minimum solutions, because we have 10 replications and the best solutions among 10 replications are improved in the bold values with the corresponding step. And finally, when we apply decomposition algorithm, we will have small improvements, but in some of the instances, we will have again better best solutions. Of course, we know that when we have more number of facilities, we will have less amount of CO2 emission in our distribution system. For the instances with 75 customers and up to 15 facilities, the computational times are shown in this table. Again, we have the fastest step as the location allocation step, and then we have transfer and decomposition step. We see that in most of the instances, we have better solutions obtained by the transfer algorithm over the applied over the location allocation algorithm. The thing here is that I should say we have up to 90% and this is significant improvements that we have with the location allocation algorithm, but 25% improvements with obtained by the transfer algorithm is also satisfactory. At the end, we have tiny improvements with the decomposition algorithm. In some of the cases, we have better minimum solutions. With this histogram, I want to show that when we apply decomposition algorithm, the number of solutions with the less objective function values are higher, which correspond to the decomposition algorithm. Of course, we solve instances with higher number of customers, with, for example, 287 customers and up to 30 facilities. With these computational times, we see that the location allocation algorithm, as well as the other improvement algorithms, have much computational times in each step. And we see that again with the transfer algorithm, we will have even although we have small improvements, but we can improve the best solution again, and this is important for us. And we have in some of the cases and instances the best solution obtained by the decomposition algorithm at the end of our algorithm. But here one can say that instead of the algorithms that take much time, we can do many and more replications with the location allocation algorithm, and we thought about that, and we did analysis with restricted times when we just have 10 minutes of solution time, and we do our algorithm with location allocation or transfer over that, and with 3 steps. We will have a different number of, we can have different number of replications, but in this table, I can say that even with less number of replications with transfer and decomposition algorithm, again, it is satisfactory for us to apply transfer for the user that wants to get the solutions soon. I will go over this table that is similar to the previous one. But remember that we had...
Arsham, would you wrap up in 5 minutes, please?
Sorry?
in 5 minutes. You can
Okay.
wrap up.
So remember that we had nonlinear function for our objective function, but we can show that with any k integer values for the nonlinear parts on z v to the power of k. We can have second order cone formulations. For example, for the applications of the aircraft, helicopters, and robots, we can have this, and we can handle it with second order cone programming formulations. For example, if we have a function as mu z vo to the power of gamma in the literature that is introduced for the robots, we can have an application in the assembly line. For example, here we have an assembly line with 20 stations, and we have a strict limited area for the depots from which the rail-guided vehicles will feed the stations. These rail-guided vehicles can have different frequencies, and for this application also we can use the multifaceted Green-Weber problem with a specific formulation, and many features, for example, time speed limits for the rail-guided vehicles we can introduce, and we can solve the problem also with capacitated depots. And when we have capacitated depots, we may have conjunction in the rails, and we handle this with some constraints. And up to here, we published our study at 2020, and I give the reference here. Just I will give you some other study predictions after this conclusion. We gave second order cone programming for Green-Weber problem and time-dependent Green-Weber problem. For the multifaceted Green-Weber problem, we provide MISOCP formulations that are weak, but we provided algorithms. And these are the studies under green transportation. About the green warehousing, that is my other interest area. In the warehouses that are forklifts doing the material handling jobs, we have order picker forklifts that can perform this job with an order picker and can move in the narrow aisles and can reach to the high levels. What happens here? For example, when the forklift is going to pick the boxes, it can go in this way and pick the boxes in 1, 2, and 3, and so on. So the way in this way we will have several vertical movements, but in a way that we in this way with less vertical movements we may have saving in energy consumptions. We provide MIP formulation for the energy minimizing forklift routing problem. And just an example here, I will give you that this problem is also hard to solve. For example, for an instance with 14 customers, it can be solved in 5 minutes, but we will have 10% saving. So this is another study that is submitted to a journal, and we are now in revision step. And these are some of my references. And thank you. It's over.
Well, thank you very much, Arsh. Well, I barely listened to you because I have a poor connection. Sorry about that. But now I wanna set the floor for questions. Mahmut Ali Hocam, are you there?
Yes, I'm here.
Yeah. Well, would you please, manage these questions and answers for me?
Okay, if I can, sure. You mean manage? Oh, okay.
Yeah,
let's. Okay, I got you. Yeah. So thank you, Arsham, for the presentation. So at this point, we'd like to get questions from the listeners, if they have any, to our speaker. We have some time for it, so I actually can open up the floor. Arsham, what I'd like to ask is, and correct me if, of course, if any misunderstanding. You're looking at this problem and its extensions, and you show that it's a difficult problem, and through some modeling and solution methodologies, you show how you improve the solution time, right, for the larger instances, basically. What I want to ask is about the real problem itself. Although you mentioned what kind of applications it could have, I might have missed it. Can we elaborate a little bit on what kind of practical situations this problem applies to? And from there, what I want you to go very, very shortly is that there are operational problems and there are design problems, right? So design problem being, for example, operational problem being solved over and over again with different data sets, and design problems is how you design a supply chain network, for example, right? And so do you consider the problem you work on more of a design problem or an operational problem? And even between those two, if it's an operational problem, there are operational problems that need to be solved very quickly. So what's the typical size of the applications in this case for this problem?
Okay, that's right. I think an operational, again, application of this problem can be such assembly lines that are designed in strategic level decisions. For example, an assembly line, an automatic assembly line of, for example, a type of cars. So this is a strategic level for some years that is designed to produce this car type. So we can use this model and this problem for this design, but also other applications of this problem can be, for example, for the jobs done by the drones. For example, I saw a problem which determined the locations of the facilities for drones, and the drones can go and satisfy the demands of the customers, and the facilities can be also located on the plane, I mean in the continuous area, not on the network. Okay. So I can just give these examples for the applications.
So I understand it's more of a design problem then, right? Not an operational problem, but a design problem.
Yes.
In real life situations. So design of a new assembly line, location of the new facility. Well, what about the size? So the sizes that you're trying to solve versus how that size would relate to a real life problem.
Yeah, we could here just solve problems up to 287, for example, customers with 3 facilities. But yeah, these instances even take much time to be solved. But yeah, it's just dependent. It depends on the applications that can be, for example, with less customers or facilities. Yeah, as you say, it is a design problem, and in each application, it can be solved easier, or in strategic levels, of course, it can take time to design the solution.
Okay. Okay. Thank you. Because if it's a design problem, then there's more room for larger solution times. Was my point. So okay. Okay. Well, thank you very much. Any other questions from the audience?
I have a question. May I?
Yeah, sure, Hocam. Go ahead.
Arsham, thank you for your presentation. It was a clear and nice presentation. What I would like to ask is the real-world applications. In your model, the distance is measured with I mean, you use the Euclidean distance, right?
Yes, Euclidean distance.
And what about Manhattan distance? Why don't you use that? Or can we use or include Manhattan distance to define an extension? Because as far as I see, for example, the applications in the warehouses, probably we need to use the Manhattan distance.
Definitely, yeah, sure.
Of
Is
course.
there any difficulty to use the Manhattan distance?
It can be, of course, used in this problem, but actually I didn't think about that. But yeah, it can be a nice extension for this problem and the future direction for this problem. But just I want to say that the problem in the warehouse is totally different from the previous problems. I couldn't explain it well because of the lack of time. Yeah, it is just energy consumption. I mean, minimization of energy consumption for the forklifts with acceleration, deceleration, and friction forces. But coming back to your question about the Manhattan distances, of course, it can be an extension for the problem. And
Okay.
it can also have a better and wider applications.
Any
Okay.
other questions? May I?
I'm sure, Hocam, I think we don't have any other questions for now.
Okay, thank
Go
you.
ahead, Adalet Hocam, go ahead.
Okay, thank you. Another question is that instead of using the Euclidean distances, because if we use the Euclidean distances, it's only reasonable if we use the helicopters or drones, right?
Right.
But if you consider the car or trucks, then it's a little bit, how to say, unrealistic, right?
Yes.
And moreover, the location of the facilities directly, how to say, identified or determined depending on the coordinates, right? But in the real life applications, that coordinate may not be a reasonable place location. So how can we handle this problem?
Yeah, for that problem, we should introduce another problem on the network and the potential locations for the facilities. I think you are pointing that. And of course, yeah, with in the real world, when we use vehicles, cars, so in that application, also we can use a networks that the distances between the nodes are known, and it can be any type of distances, even with Euclidean distance or other type of distances. So the distances in the networks are known. So we can just shift to the discrete type of this problem. It can be also considered.
Okay. Thank you. Last question. You convert a very sophisticated, complex, nonlinear programming problem to a more manageable one, two-order comp problem, right?
Yes.
It's really good. I like it. But how did you solve this this problem, new converted problem? I mean,
okay. So
what's the tool?
So the solvers, for example, such as Cplex or any solver that solves linear programming formulations, they can solve second-order comprogramming formulations. As I said, with polynomial time.
Okay.
So there is no need for nonlinear solvers or a specific solver. All of the solvers that we use for linear programming can solve second-order comprogramming.
Okay. Thank you very much. That's all. I'm done.
Okay, thank you, Adalet Hocam. Yes, next question.
Mahmut Hocam, may I?
Yes, go ahead, please.
Okay, Arsham, thank you so much for the presentation. I have a more general conceptual question. As a decision variable, you assume constant speed for each vehicle. I wonder whether it would work to change the speed dynamically within time. If you think that it is worth to do that, as the second question, how can we solve such a problem?
In our problem, as I understand you well, in our problem, the speed variables or the speed amount are variables.
Yeah, variables, but constant within time. You are not changing it dynamically. You assume v sub I for vehicle I, right? And it is a constant speed.
Yeah, it's constant speed from the facility to the customer.
Yeah. My question is, would it work to change the speed dynamically within time?
Very nice question, and it can be also considered. But just close to your question, we just use time-dependent speed limits, and yes, these are just limits. But we can also yes, consider speed variables varying on the time also. I have no idea just now for that.
Yeah, do you think that it would improve the optimal solution? I don't know, maybe it adds something.
Okay, in that way, I can say no, because the problem or the formulation just tries to make the speed variables close to the optimal speed, where we have the optimal speed. So any deviation from the optimal speed will cause in the worst objective function value. So in all of that path from the facility to the customer, if we have constant speed tried to be close to the optimal speed, I think it will result in better solution.
If I may interject, maybe I understand they assume an average speed for the whatever is if it is the vehicle or the drone. So the only one way that speed might be a decision variable is if these are battery powered. If we are especially talking about battery powered vehicles, might be otherwise too. You don't have to go at the maximum speed limit, but speed might be connected to the energy efficiency somehow. And so that might be a decision variable on its own on how fast it should go, because the faster you go, the more energy you would spend to do the same thing per distance, for example. That might be one way.
Of course, that's right, Mahmut, because I studied a little bit also on the electric vehicles, normal vehicles, but with electric energy consumption. So in those applications, the function of the energy consumption is not like this, not at all. So as you said, we don't have optimal speed in those applications, and minimum, let's say, minimum energy consumption or convex, let's say, function for that. In those applications, electric vehicles, we have just increased energy consumption with increased speeds.
Yes. Yeah, that might be one thing, so that there's a maximum speed limit, but if there's no traffic issue, then the speed might be a decision variable on its own. Okay.
Thank you, Arsham and Mantel Hocam. Thank you.
Yeah. Okay. Any other question from the audience? Well, I guess that's it. Arsham, thank you very much for your time. We already went over the time limit a little bit for the seminar, but it's been very interesting. Thank you and good luck again. Seems like a very difficult problem with many extensions. Just as a final check, if there are no more questions, I'm going to thank my speaker and send him on his way. Well, thank you, Arsham, and I hope to see you again soon. Yeah.
And if no question, I just only hope that I wish that my presentation went well with the restricted time, and if I had presented in just a nice way, I'm happy for that.
Yeah.
Well, and nice to meet. I'm very happy to meet new, let's say, friends and new people in academy, and hope to see you again.
Yeah, come to Izmir for more than 4 hours next time. Okay.
Right. Yes.
Okay. Sinem,
Thank you very much, Arsham.
Yeah.
You're welcome. Thank you too.